Think about the world around you for a second. Picture that massive engine block sitting under the hood of your car, taking thousands of explosions every single minute. Now, picture a tiny, perfectly contoured dental crown sitting in your mouth. You're probably thinking, what could those two things possibly have in common? Well, it turns out they share a pretty dramatic, fiery origin. They were both born from liquid fire. Today in The Explainer, we're diving into the absolute bedrock of modern manufacturing, casting. We're going to look at how taking solid material, completely melting it down, and trapping it in a brand new shape is literally the foundation of modern engineering. We've got 5 quick stops on our journey today. First, an intro to casting. Then we'll weigh the capabilities and disadvantages. Third, we'll look at big and small applications. Fourth, types of molds. And finally, we'll go inside the foundry process. Let's get right into it. Section 1. Introduction to casting. Okay, let's establish exactly what we're talking about here. At its core, casting is a story of total physical transformation. It's a process where a perfectly solid chunk of material is completely sacrificed to a furnace. It gets melted, heated up to a very specific, incredibly high temperature, and then, using gravity, a vacuum, or intense pressure, that literal liquid fire is forced into a hollow cavity called a mold. The metal gets trapped inside that shape, cools down, and solidifies. And a quick heads up, the word casting is pretty versatile. We use it to describe this whole violent, dramatic process, but we also use it to name the final physical part that pops out at the end. Now, here is something that absolutely blows my mind: the timeline. We rely heavily on casting to build our ultra-modern technology today, right? But it's actually one of humanity's absolute oldest shaping processes. The roots of this fiery art go back roughly 6,000 years. That is 6 millennia of humans manipulating molten material to build their world. Section 2. Capabilities and disadvantages. So you'd think after 6,000 years we'd have it absolutely perfected, right? Well, let's weigh the pros and cons to see why heavy industry still relies on this ancient method. First off, the capabilities are massive. You can create insanely complex geometries. And I don't just mean the outside shape. Casting lets you create intricate internal hollows that would be pretty much impossible to carve out of a solid block of metal. Plus, depending on how you do it, you can achieve what engineers call net shape or near net shape. That just means the part comes out of the mold already looking the way you want it to, with almost zero extra shaving or machining needed. Combine that with the ability to make huge parts, and you've got a process perfectly suited for mass production. But let's be real, it's not all perfect. Let's look at the gritty reality of the factory floor. Casting has some serious drawbacks. For one, the structural integrity of a cast metal piece sometimes has weaker mechanical properties compared to forged metal. You might also run into poor dimensional accuracy or a really rough surface finish, especially with older methods like sandcasting. But the absolute biggest flaws? The human and ecological costs. This process involves severe safety hazards for the workers. They are literally operating alongside rivers of hot molten metal. Plus, the extreme heat, the toxic fumes, the chemical byproducts, it all creates serious environmental problems that the industry has to constantly battle. Section 3. Big and small applications. Keeping those pros and cons in mind, let's look at the unbelievable versatility of what this process actually makes. Keep in mind, you can cast pretty much any kind of metal, whether it's ferrous, meaning it has iron in it, or non-ferrous. Because of that, the sheer scale of casting is just breathtaking. On the massive side, we're talking the backbone of our infrastructure. Huge engine blocks, towering machine frames, railway wheels carrying thousands of tons of freight, and even giant ringing church bells. But then, using the exact same foundational principles of melting and molding, we make tiny, intimate things. A dental crown perfectly matched to your tooth. Delicate jewelry. Small statues. Even the frying pan you use to make eggs in the morning. From a massive locomotive to your kitchen table, casting literally touches everything. Section 4. Types of molds. Now, none of those things would be possible without the true unsung heroes of this whole operation, the molds. How do we actually shape the liquid fire? Well, it basically comes down to a trade-off between 2 main types of molds, expendable and permanent. With an expendable mold, the mold itself is completely sacrificed. You literally have to break it apart to get your part out. The huge advantage here is geometric freedom. You can make wild, complex shapes because you don't have to worry about pulling the part out of the mold intact. The downside is that it's slow because you have to build a brand new mold for every single casting. Permanent molds, on the other hand, are made of metal and reused over and over. That gives you a huge boost in speed and production rate. But the catch is, your geometry is strictly limited. You have to be able to open the mold and pop the solid part out without breaking it. So you're always balancing speed against complexity.
Section 5. Inside the foundry process.
Okay, let's step right onto the factory floor, the foundry, and see what the skilled workers, known as foundrymen, are actually doing. As you can see brilliantly illustrated here in this sand mold cross-section, you've got the pouring ladle tipping over, funneling that molten metal right into the downsprue. The liquid fire travels down and completely fills the mold cavity. You'll also notice the parting line running right across the middle. That's where the two halves of the mold meet. Once everything cools and solidifies, you get the solid casting you see on the right. But notice how it still has those extra bits attached, the sprue and the runner? That's leftover metal that's solidified in the pathways, and that all has to be trimmed off later. It's just a fantastic look at the raw mechanics of the pour. Even though the physics are extreme, the actual steps in a foundry are surprisingly straightforward. It's a really satisfying 6-step cycle. Step 1, you melt the raw metal. Step 2, you carefully pour that liquid fire into the mold. Step 3, you wait. You have to allow adequate time for the metal to cool and completely solidify. Step 4, and this is for the expendable molds we talked about, you break the mold apart to retrieve your casting. Step 5, you clean and inspect the part, which includes separating it from that extra gating system we just saw. And finally, Step 6. Depending on what the part is for, it might need a final heat treatment to really lock in its metallurgical properties. So it's melt, pour, wait, break, clean, and treat. The whole shebang. Which brings us to the end of our journey today and leaves us with a pretty massive question to ponder. We still heavily rely on this 6,000-year-old process to build everything from railway wheels to dental crowns. But how are the foundries of tomorrow going to evolve? How will modern engineering adapt to eliminate those severe environmental and safety hazards that come from working with literal rivers of molten metal while still keeping up with our global demand for mass production? It's a fiery challenge the industry's facing head-on every single day. Thanks for joining me on this explainer, everyone. Keep asking those big questions, and we will catch you next time.